When you're talking about pressure, you first must make the distinction between an open and closed system. For the most part, whenever you view a fluid in your everyday life, you're most likely looking at an open system. We call it an open system because there's really nothing on top of the fluid except the atmosphere pushing down. There's no lid or covering providing additional pressure. In a closed system, the fluid is completely sealed off to outside pressure, which means you really can't see the fluid even though it's there. A hydraulic lift at an auto repair shop is the perfect example of a closed system. In fact, a car has several closed systems in the power steering and the power brakes. But again, you don't see the fluids because those systems are, of course, closed. So here's a side profile of a reservoir and a dam, which of course is an open system because there's no lid on top of the water. To calculate the pressure of the fluid at the bottom of the dam, we simply use the equation the density of the fluid times gravity times the height, which is very similar to the potential energy of any falling object, which is the mass of the object times gravity times the height. They're similar because in both cases, objects are in the air away from Earth and gravity is pulling them down. So since when we're talking about fluids, the force of gravity and the density of the fluid are generally constant, that means the only variable we really have is height. And we can see the difference that height makes in creating pressure by comparing two different kinds of dams. On the right, we have the Hoover Dam. It's enormous, several hundred feet from the top of the reservoir down to where the water shoots out. And that creates enormous pressure when the water is released. On the water on the left, the height is only a few feet. Consequently, the water doesn't come off the reservoir with very much pressure. If you live in an area without a lot of hills or tall structures, you may see water towers spread throughout your town. The purpose of water towers is to create pressure. And again, since the equation is density times gravity times height, by increasing the height of the water, you increase the pressure in the pipes. When you're analyzing the height of a system in order to calculate the pressure, we really don't care about the height of the system as a whole. Instead, all you care about is the difference between the beginning and the end point. In this picture, the beginning point is the height of the reservoir. The end point, well, that actually depends on where the water is being used. If you're on the third floor using the toilet, you don't have a lot of height and you don't have a lot of pressure. On the other hand, if you're on the first floor using the sink, you end up having a lot more height. Consequently, you have more pressure. Everything we've seen up till now has been an open system because one end was open, allowing water to leave the system. When you have a system where water is not allowed to leave, when everything is sealed up, then you're dealing with a closed system. And when you have a closed system, we can use Pascal's law. To understand Pascal's law, you first have to understand a new definition of pressure. And that is that pressure is equal to the force being applied divided by the area. Pascal's law states that when you apply force to a closed system, that creates pressure, and that pressure is evenly distributed throughout the system. That means that when comparing any 2 points in the system, the force divided by the area of the first point is going to be equal to the force divided by the area on the second point. A key to hydraulics is that different points have different surface areas. So, by manipulating the surface area, you can also manipulate the force. Bernoulli's principle simply states that as the velocity of a fluid increases, the pressure of that fluid decreases. The most practical application of Bernoulli's principle is in aircraft. If you look at the cross-section of a wing on an airplane, you'll notice the wing is curved. By curving the top of the wing, we create a longer distance that the air has to travel as it goes over the top of the wing compared to the bottom of the wing. Because the air has a longer distance to travel, the air on top ends up going faster. According to Bernoulli's principle, as air moves faster, the pressure drops. So on the top part of a wing, you have a low pressure zone. On the bottom part of the wing, because the air is moving slower, you have a higher pressure zone. And that high pressure pushes the wing up. There are several simple experiments you can do to demonstrate Bernoulli's principle, including taking a sheet of paper and blowing across the top. As you blow across the top of the sheet of paper, you create a low pressure zone because the air is moving faster. So you have a low pressure zone on top and a high pressure zone below the paper, and the result is the paper is pushed upward just like an airplane's wing. So here's a problem that's asking us to combine a couple of different factors that we know about pressure. We know the equation for pressure is simply density times gravity times height. In this situation, we have 2 points, B and C, that appear to have the same height because they're both the same distance from the top of the tank. Ordinarily, you would think if they had the same height, they must also have the same pressure. The difference in this case is that since water is being allowed to leave the tank, and that water is moving the fastest at point C, then Bernoulli's principle kicks in, which states as velocity increases, pressure decreases, which means the movement of the fluid is creating a low pressure zone, meaning that B is going to have slightly more pressure. If you're ever asked a question about a closed fluid system, such as a hydraulic lift, then you're likely going to be using Pascal's law. And remember that Pascal defines pressure as the force being applied divided by the area. And Pascal's law says that when you apply pressure to a closed system, that pressure is evenly distributed throughout the system. In other words, the force divided by the area is equal to the force divided by the area at any 2 points. In this case, we have a closed system with 2 ends that have different areas. The left-hand side has a radius of 5 and the right side 10. To figure out what is the area at either end, we can use the equation that the area is equal to pi times the radius squared. So the left-hand side is going to have an area of 25 pi, and the right-hand side will have an area of 100 pi. Now we can just use Pascal's law to set up our equation. The problem states that a 5 kilogram force is being applied to the left, and the area we figured out was 25 pi. And that's going to be equal to the force on the right that we don't know yet, divided by the area on the right, which is 100 pi. Cross multiply, and we get 25 pi times F is equal to 500 pi on the right. Divide both sides by 25 pi, and we get the force is equal to 20, or enough force to lift 20 kilograms.